Let's continue in 1.2. This is on the implicit function theorem. What we call this is an existence theorem. So it doesn't tell you how to find a solution or the concept, but just tells you that this function exists. Now this actually doesn't have to do directly with differential equations. This is a more general concept that you can find a function that behaves this way. But let me show you what this has to do with. So this is talked about in example 30. It doesn't really matter. No need to really dive into this, but I need to show you what this is talking about. So first, let's let g of xy have continuous partials in, and then it's defined in a rectangular region. So R is equal to the region or the set xy such that a is less than x less than b. So it's open, right? Because I'm not going to those edges. C less than y less than d. So that's a rectangular region with x naught, y naught in that region R. So if g of x naught, y naught is equal to 0, and the partial of g with respect to y of x naught, y naught does not equal 0. So remember, it's kind of a typical assumption, right? We don't want that partial to be 0. Then there exists a differentiable function y equal to phi of x defined on the open interval x naught minus delta, x naught plus delta, right where delta is a small positive number, and g of that function phi of x is equal to 0 for all x in I, in that interval, that open interval. So it's basically saying that the existence of this function to make this implicit form of the function true. So the implicit form, let's go back here, is this, so that when you substitute in, you get a true statement. And that's kind of what we're doing back here, right? We're able to take this form and substitute in and get a true statement. Okay, so that's the connection between the two. So they continue with an example, and I'm just going to cover it, but I don't think we need to at this point. So let's go on to initial value problems. Okay, so initial value problems is kind of where we're heading, kind of more important. This is really important, but it's just a little more advanced to continue that discussion. So let's look at initial value problems, and we'll kind of roll with that one. So initial value problems. And it should have a bit more familiarity with this one. This is definition 3. All right, so I'm going to change up what they're saying to my own words. Right, so given the differential equation ODE fx y. So this is equation 1 above, basically. We'll just say y prime, etc., to yn. Make it simple on us. Okay, so given that differential equation of the nth order, solutions on an interval I we have, sorry about that, this statements that satisfy the different components. So we have y of x naught equal to y naught. We have dy dx of x naught equal to y1, etc. And we have dn minus 1 of y dx n minus 1 of x naught equal to y sub n minus 1. So we have all those different solutions or initial conditions where x naught is in I and y naught through y sub n minus 1 are given conditions. Right, and that's what we mean by initial condition or given conditions. Like you say, this is where we're starting. So that's how it's defined. And again, this is, just kind of getting used to notation, the form, and this kind of reminds me a lot of I don't know, maybe Calc 1 stuff where it's a bit of theory and then you're just like, well, you got to do the problems. You got to jump into this and do some problems. So that's the initial value problem, basically finding solutions to this form. The next theorem is theorem 1, and that's on really what we'll be doing, and this is an existence theorem, so existence and uniqueness of solutions. So theorem 1, so technically the first theorem in the book they're going to talk about, more or less, says suppose that dy dx is equal to f of xy and y of y naught is equal to, y of x naught is equal to y naught. Okay. If f, that's a period then, if f and partial f respect to y, and then, that's usually going to be a d, but it's okay, are continuous functions, are continuous functions on R. So this will be the same R defined above, basically. So R is that rectangular region. So all ordered pairs x, y such that x is between A and B, and y is between C and D. So it's an open rectangular region. And you have x naught, y naught in R. then phi of x is a unique solution to that differential equation, to this whole thing. And it's true, so it's that statement. So given that initial condition here, oops, sorry, sometimes it does that. That's the initial condition, so you get that that's a unique solution, the equation itself, for x in I, and I is that open interval x naught minus delta, x naught plus delta. And of course, delta is a small, usually considered a small positive number. Okay, so the proof of this, so normally you do a theorem, then you do a proof, because it's the first theorem technically. This is in chapter 13, which I'm not sure this book goes to 13. It's the other book, maybe, I don't know. Or advanced calculus talks about that proof. So, so that's an existence concept and uniqueness. Basically, what that's referring to is what we just did back here. So, examples, what was it, 4 and 10, we're finding the solution. We're finding phi of x that gives you the solution. So it's saying when you find this solution that it's a unique solution. And then if you have a particular value, then it's a particular solution to that differential equation. And then let me bring up the function. Let's see, here it is. I'll copy that over just to have it in the notes. All right, so this is what the basic picture would look like for the solution. So you can see, so here's your x value, here's your y naught value, and then here's your open interval. All right, so here's a rectangular region that's defined on, like that. That's your R. Okay, so R is all the blue. And then here's your open region for your delta. So that gives you that. And then, so phi is basically a solution anywhere in here. So that's your phi of x. Okay, so the problems are pretty straightforward so far in 1.1, 1.2. 1.3, talk about briefly. I'm not going to spend time on that. So that's on your own. Just look at, or go straight to and look at problems assigned. Problems homework only. I assigned a couple just to take a look at it. It has to do, it's almost like a contour map that we did in Calc 3, where you have the projections and the. So when you solve these differential equations, and we'll see this later, you'll see that you have multiple solutions because you're going to be integrating. We haven't seen one quite yet, but you're integrating, you'll have arbitrary constants. So if it's not an initial condition and you have arbitrary constants, then you might get multiple solutions that look like that, right? And so some might be like this, and then the other ones start being curves depending on what your C value is. So that's what it's about. Okay, and I'm not going to spend too much time on that. Next, so we wanted the last part of this chapter, which again goes pretty quick, is 1.4, and we'll look a little bit at the approximation methods similar to Newton's method.